Welcome back, children. I'm Srinivasan here. We are going to discuss about the chapter 1, relations and functions. In this, we are going to discuss about relations today. Before going for relations, we should have an idea about Cartesian product. Cartesian product, you would have studied this in 11th standard. If you are given with two non-empty sets, if you are given with two non-empty sets, A and B, then the Cartesian product A cross B is defined as A cross B is defined as set of all ordered pairs of elements from set A to set B is a set of all ordered pairs from set A to set B. Say for example, set A has elements 1 and 2. Set B has elements 3, 4, 5. Then the Cartesian product would be defined as 1, 3, 1, 4, 1, 5. So A cross B, the Cartesian product A cross B is defined as the order pairs 1, 3, 1, 3, 1, 4, 1, 5, and pairing this 2, we get 2, 3, 2, 4, and 2, 5. Okay, children. This is the Cartesian product. All possible ordered pairs from set A to set B defined as Cartesian product. Okay, children. Now, I am going to define a relationship now. Now we are moving to the topic relations. Now I define a relationship between these two sets, defining it as R is a set of all order pairs x comma y such that y is divisible by x. Okay, I define the relationship as the set of all ordered pairs such that y is divisible by x. Now you see here 3 is divisible by 1. Yes, it is true. So we will take that order pair 1, 3. Y is divisible by x. So 3 is divisible by 4 is divisible by 1. Then 5 is also divisible by 1. 3 is not divisible by 2. But 4 is divisible by 2. 5 is not divisible by 2. So I defined a relationship between x and y as the set of all order pairs satisfying this condition y is divisible by x. From this we can understand Cartesian product is set of all possible order pairs, whereas the relation R is a subset of the Cartesian product. Can you understand? Because you have taken 4 order pairs from this one, but leaving out this 2, 3 and 2, 5. So relation can be called as a subset of the Cartesian product. That you should understand, children. Okay. Now, let us write a small definition for a relation. Take down. A relation is defined as a relation R from a set A to a set B is a subset of Cartesian product A cross B obtained by defining a relationship between the sets or between the first element x and the second element y of the order pairs in A cross B. So this is the definition, children, for a relation. So at this moment, we understand that a relation is a subset of Cartesian product by defining a relationship between the elements of the order pair. Okay, children. Now we'll take another one example. I'm erasing it. A set contains elements from 1 to 6. Write down a set A which has elements from 1 to 6. Now we'll define a relationship from A to A. Define a relation from A to A such that R is equal to set of all order pairs x comma y such that y is equal to x plus 1. Okay, children. Now let us see what are the order pairs possible in or satisfying this relationship y equal to x plus 1. Take the x value, x is 1, what will you get for y? Yes, 2. Take next x, 2 plus 1, 3. Next take the input, 3, you'll get 4. Next, 4 plus 1, yes, 5. Substitute 5 the place of x, 6. Now you cannot substitute 6 because 6 plus 1 is 7, which is not in the set. So these are the order pairs of the relation R, which comes under this definition, relationship y equal to x plus 1. Okay, children. Now some terms we will know. The domain of R is the set of all first elements of the order pair. Similarly, the range of R is set of all second elements of the order pairs. In the relation. Add the word in the, because we didn't mention anywhere the relation, the word relation, so we'll write it down. Okay, children. Now the image of element x, image of an element x under a relation R is given by y, where the order pair x comma y belongs to R. So these three definitions you must know. Okay, children, regarding relations. I hope up to this we have some idea. Doing problems will help us to understand much better. Okay, children. Now, next topic we are going to see types of relations. There are three types of relation, children. One is empty relation or void relation. Number two, you have universal relation. Number three, you have equivalence relation. Okay, children. First one is empty relation, or we call it as void relation. Second one is universal relation. Third one is equivalence relation. Empty relation, the definition will not allow us to write any order pass in the relation. It's an empty relation. For example, I am taking a relationship defining the number of students in a boys school. If I am defining number of girls in 10th standard, it would be empty relation, because in boys school there won't be any girls, so it is not possible. So such cases is called as empty relation. Or we'll take another example. I take a set A which has elements 1 to 4. I define a relation that the difference between the elements should be 10. Say for example, I take A as 1, 2, 3, 4. Now I define a relation set of all order pairs such that x minus y should be equal to 10, which is not possible because no difference can be equal to 10. So such relations are called as empty relation. This is an empty relation. Okay, children? Okay. So this is an example for empty relation. Next one is universal relation. Universal relation, all possible order pairs should be there in your relation. Then we call that relation as universal relation. First, we'll write a definition for empty relation. A relation R in a set A is said to be, or it's called as empty relation if no element of A is related to any element of set A. No element of set A is related to any element of set A. As I told, the two examples I told you, I hope you would have understand empty relation. Now we'll move on to universal relation. So as I told you, universal relation, all possible order pairs should be there in your universal relation, or in short, Cartesian product should be equal to your relation. Such a way you define a relation. Okay. Say for example, I say a relation A is equal to, the same example I have taken 1, 2, 3, 4. Now I define a relation or set of all x comma y such that the difference between A minus B should be greater than or equal to 0. The modulus of the difference between A minus B should be greater than or equal to 0. So we all know the modulus function will convert the negative value to a positive value. Always the output of this function would be a positive value. It will be greater than 0. So this is always true. So here the relation R will be A cross A. That is your Cartesian product. Such relation is called as universal relation. In this case, R is equal to A cross A. Your Cartesian product is equal to, here the set A is defined to A itself. Okay. Now let us make the definition for universal relation. Sorry. A relation R is said to be a universal relation if each element of A is related to set A. If each element of set A is related to every element of set A. That is the meaning of R equal to A cross A. Okay, children. I hope you got that. Very good. Now, this universal relation and empty relations are called as extreme relations. These both are also called as, collectively they are called as extreme relations or trivial relation. Why they are called as extreme relation? Extreme means either to this corner to that corner. Here you see empty relation, nothing will be there. That is one end. Universal relation, you have all the possible order pairs. So that's why they are called as extreme relations or trivial. They are very particular. So that is about empty relation and universal relation, children. Now we need to know about equivalence relation. If you want to learn equivalent relation, you should be familiar with these three terms: reflexive, symmetric, and transitive. Mostly 4 mark questions coming from relations or from proving that equivalence relations only. Most common. Okay, children. Now let us see equivalence relation in detail. I am erasing this part. Shall I erase this? Okay. Children, in book it is given in very detail. I have taken only the crispy points which will help you to understand better. That's why I made a small notes regarding to this one, which will help you. Now, the first part, as I told you, we must, to learn equivalence relation, first we should learn reflexive, symmetric, and transitive. Now let us see what is reflexive. Now we'll write the definition and then we'll go for the discussion. A relation is said to be reflexive if for every x belongs to set A, the order pair x comma x belongs to the relation R. So A is a set, R is a relation. Okay, children. For example, we'll take an example. I say set A as 1, 2, 3. Now my relation R has 1, 1, 2, 2, 3, 3, and 1, 3, 2, 1. Like this. I want some relation basics. I got this order pairs in my relation. Now we need to find whether this relation R is reflexive or not. So see the elements of the set A. It has 1, 2, and 3. If x belongs to A, then x comma x should belongs to that R. Then we will call it as reflexive. It's like a reflection. So 1, if you take 1 comma 1 is there. X, if you take x comma x is there. So 1 I have taken, 1 comma 1 is there. So its reflection is there. See the next element 2. 2 comma 2 is there. Next, you are good. You are correct. If you take 3, 3 comma 3 is there. You may have extra order pair. That doesn't matter. But you should have the reflexive of the all the elements whichever is given A. That's why for every, this word is very important. So every element, if I have 4 and 5, then I should have 4 comma 4 and 5 comma 5 in the relation. Otherwise it is not called as reflexive. If I don't have this 3 comma 3, I have these things, this is not called as reflexive. So every element should have its reflection. So I hope you would have understood this very easily, right? So learning reflexive is very easier. Okay. Again, you mean this is set and this is relation. Second one, we go for symmetric. We'll see. We are going to see a lot of examples related to this in the problems. Now, a relation is said to be symmetric if for any element x belongs to a set A, two elements, symmetric, right? X comma y belongs to set A, then x comma y belongs to R, implies y comma x should be there in R. First you should check x comma y should be there in A, then the order pair x comma y should be there in R. Then you should, if you want to say this relation is symmetric, then you should compulsory have y comma x should be there in the relation. Take one example. I am taking a set A with the elements 4, 5 and 8. Okay children. Now I have defined some relationship. R is equal to, I got these order pairs in my relation 4 by 5 comma 4, 8 comma 4 and 4 comma 8. Now we'll check whether this is symmetric or not. You see that two elements x comma y, you choose from A. It has to be from A. So 4, 5 is there in the set A. First point is getting over. Okay, confirm. Next, x comma y belongs to R. Yes, 4 comma 5 belongs to R. Then you should have y comma x belongs to R. You have to check for 5 comma 4 is there or not. Yes, 5 comma 4 is there. Okay. Now itself you cannot say it is symmetric. We should check other order pairs. Now I go for 8 comma 4. First I say 8 comma 4 belongs to set A. Yes, it is there. Then the order pair 8 comma 4 belongs to R. Then I should have 4 comma 8 in the relation. Yes, I have 4 comma 8. So this relation is symmetric, no doubt. Now you should see the word for any here, for every element should have a reflection. That is why reflexive for any. See children, we may have number of orders, still we have number of order pairs. You can also have 5 comma 8, but I have not included 5 comma 8. Can you see that 5 comma 8 is there? You should have 8 comma 5 in, then only we call it as symmetry. So there are some order pairs which are left alone, which are not included. So all the possible orders of the relation is also not included here. So we may have some order pairs which is not included. That's why we say whatever you are taken from the relation, you check the condition and you call it as symmetry. So it is not compulsory you have to check with every element, but here in the reflexive case you should check for each and every element you have a reflection. You understand children? Likewise you may have number of combinations of order pairs which is not included in the relation. That doesn't matter, still it is symmetric. Okay children, that's why it is given as for any. Okay, shall we move on to transitive? Yes. Okay. I hope you are following me, children. Okay. Now, the third one. A relation is said to be transitive if for any. I hope you would have understood for any and for every the difference. If for any elements, here also you can include yes. X comma y comma z. Now we are going to take 3. Reflexive one element. Here we have taken 2 elements. Now we are talking about 3 elements. Belongs to set A such that x comma y belongs to R and y comma z belongs to R. Then this relation is said to be transitive. This implies x comma y comma z. Then x comma z should also be in the relation, or then only call it as the relation as transitive. Otherwise, it is not transitive. There are some important facts about transitive which I have taken separately that I will teach you after finishing this, so that you will not get any doubts in the transitive. Take for example, I have taken a set with 9, 5 and 3. Example, a set A, 9, 5 and 3. Okay children, I defined a relation R. 9 comma 5 is there, 5 comma 3 is there, then I have 9 comma 3, 9 comma 1, 5 comma 3, 9 comma 3. So on seeing it, let us check whether it is transitive or not. 9 comma 5, so 3 elements 9, 5 and 3 should be there in the set. Yes, obviously I have taken elements. You can have number of elements, but I have taken 9, 5, 3. Okay, and the relation I check when x comma y belongs to R. Yes, 9 comma 5 belongs to the relation R. Okay, it's there. Then y comma z, so 5 comma 3, some y and some z. Okay, it's there in the relation. Then you should have x comma z, the first element of this order pair, and the second element of the second order pair should get a new pair. Yes, 9 comma 5, 5 comma 3. I have 9 comma 3 in the relation. Therefore, this relation is called as transitive. That's, see children, how simple it is, right? So this is the rule for transitive. In short, we'll make everything very short. Now for any the meaning we have 3 comma 9 can be there, and 5 comma 3 I will include 3 comma 5 can be there. So there are some more order pairs which is not included here. So that's why we are not taking every element. So we have taken only a few order pairs. Okay children, the difference between. In short, when we will call it does not, the relation is not reflexive. When you say it is not reflexive, simple, there exists x belongs to A, then x comma x does not belongs to R, then you call it as not reflexive. We are learning in a negative way. Not symmetric. In short, I am making very short. This is for every. Okay, here for any x comma y belongs to A, if x comma y belongs to R, then if y comma x does not belongs to R, we call not symmetric. Then not transitive. Can you try? We should take 3 elements for any x comma y comma z belongs to the set A. Excellent. X comma y belongs to R, then y comma z belongs to R. Then if x comma z does not belongs to or, then call it as not transitive. This is negative way of learning. Some students will understand in a negative way. That's why I showed this one. They can understand this one. Okay. If you want to show not reflexive, the questions are there, not reflexive, not symmetric, and not transitive. This idea will help you to do that. Okay, children. Now, as I told you, we are going to see an important page which will help you to understand transitive better. Let us see, children, some important points to be noted about transitive relation. These are some of the doubts which I found in with the children, which I found confused in your transitive relation. Let us see. First, empty relation. Empty relation is always transitive. Here you cannot check. The important point is if you cannot check the condition, then you can take it as transitive. You cannot check the condition. R equal to A cross A. All positive order pairs will be there. Then it is transitive. Then 1, 1, 2, 2, 3, 3. This reflexive. This relation is always transitive. Okay, children. Now here see 1, 2, 1, 3 is there. Here the condition cannot be checked. If 1, 2, 2, starting with 2 is not there, or starting with 3 is not there, so we cannot check the condition. As I told you, if the condition cannot be checked, please take it as transitive. So note, if condition is not met, you know what I mean by condition. X comma y belongs to R, y comma z belongs to R, then x comma z belongs to R is a condition, right? This implies X. When this condition is not met, take it as transitive. Okay, children. Now you see a single order pairs 2, 3 is there, condition cannot be checked. So take it as transitive. Here 1, 2, 2, 3 is there, then 1, 3 is there. Obviously the condition is clearly met, so it is transitive. The last one, children, think carefully. 1, 2, 2, 3, 1 is there. You will very clearly say, sir, 1, 1 is not there. So if 1, 1 is there, we will take it as transitive. No, even 1, 1 is there, you cannot take it as transitive. Think it over. When student is writing this order pair 2, 1 first, and he writes 1, 2 next. Can you understand? Yes, 2, 2 should also be there. They understand this order pairs writing order is totally different, right? So this is not transitive. So this should include the order pair 1, 1 and 2, 2 to make it transitive. So it is not transitive, children. I hope these are some of the doubts about transitive you would have got cleared. This is about introduction of the chapter relations and functions. We discussed only relations here. Now we are going to do exercise 1.1 in the next video. Thank you, children.